Welcome to Terminal Velocity, the show where I optimize a problem until I wind up making it slower. In this season, we're going to be tackling Strassen's algorithm, a fast method of multiplying large matrices. Over the next episodes, we're going to massively optimize this algorithm until we start to regress in performance. In this episode, we're going to define our problem and write a solution, which will serve as the starting point for this performance analysis. Computers usually multiply matrices the same way a human would. For each row of the first matrix and column of the second, you multiply each element of the row by its counterpart in the column. First by the first, second by the second, etc. Then stick the sum of those products into the intersection of that row and column in your result matrix. That's the algorithm taught in textbooks. That method of matrix multiplication can also be extended a bit. We can split any square matrix M with an even height and width into 4 quadrants from top left to bottom right, then pretend that M is a 2x2 matrix of those quadrant matrices, and multiply them in the same way that we did before, just by using matrix multiplication in addition to multiply and add the quadrant matrices in each row and column. This is the recursive definition of matrix multiplication. These methods work well in most cases, but can get a bit slow when the matrices are large because you're multiplying n-cubed pairs of numbers. For example, multiplying two 4x4 matrices takes at least 64 multiplications and 48 additions, 64 being 4 cubed. However, the recursive definition can be mathematically optimized to reduce the number of multiplications. This optimization is Strassen's algorithm, which cleverly redefines the result as a sum of 7 submatrices, all which require only one multiplication to compute. This reduces the complexity from n cubed to n to the base 2 log of 7. As a trade-off, you wind up using significantly more memory and doing significantly more addition. Nevertheless, you can efficiently multiply even small matrices with Strassen's algorithm. This is the algorithm that we'll be optimizing over the coming episodes. To ensure I'm able to focus on optimization and get this done in a reasonable amount of time, I'm going to focus on multiplying square matrices with sizes that are powers of 2. But matrices with other shapes and sizes can also work efficiently with minor alterations to the algorithm. To start, I'm going to implement the textbook matrix multiplication algorithm in C. Then we'll compare this to the recursive solution and a reference implementation of Strassen's algorithm. Let's see them. Alright, this is the textbook implementation. The n-cubed runtime can be derived from the 3 for loops, and the code itself is pretty similar to how you do it by hand. I zero out the result and then add all of the row-column products into the result matrix one by one. The runtime of this algorithm is charted across various matrix sizes here. Again, it's obviously very superlinear. I'm using a log 10 y-axis here to show detail in both the low and the high range. Although the performance becomes pretty questionable as we hit matrix sizes of 1024 and 2048, it performs really admirably on small matrix sizes. In contrast, let's check out an implementation of recursive multiplication. Okay, this is the recursive solution. You'll notice that I'm stack allocating all the temporary buffers here. I'm going to do this for my implementations of Strassen's as well, because otherwise this would just be a benchmark of my memory allocator. I've also given the result buffer a restrict keyword, which tells the compiler that it's a completely separate chunk of memory from our inputs. Both of these immensely speed up the solution. The meat of the implementation happens here. The rest is just allocating and copying the 4 quadrant submatrices. The 8 recursive calls in this function show that as the matrix size doubles, the number of multiplications increases 8-fold, giving us our n-cubed runtime. If the enormous amount of memory being allocated wasn't alarming enough, our performance chart shows big slowdowns compared to the textbook algorithm across all sizes, but especially on the smaller matrices. All of the extra memory usage and copying both take time and make the algorithm much less cache-friendly. However, the extra overhead isn't nearly as pronounced on those large matrix sizes, which means we may be able to claw back to a performance win with Strassen's algorithm. Let's see if we can. And here's Strassen's algorithm. Just like the recursive implementation, there's a lot of allocation and copying going on, with the most important steps of the algorithm happening here. We only need to recur 7 times per call, once each for M1 through M7, which gives us our base 2 log of 7 runtime. We're still allocating and copying an enormous amount of memory, but there are indeed performance gains to be had here. This algorithm is faster than the textbook multiplication on larger matrices, and of course can be optimized much further. We're going to use this implementation as a reference and optimize the heck out of it in the coming episodes. Next time, we're going to significantly improve our implementation of Strassen's algorithm by, not doing Strassen's algorithm as much. Trust me, it'll be great. Until then, thanks for watching. Be sure to smash that bell and comment if you have any questions or suggestions. See you next time.